Okay, welcome back. Today we're going to talk about selective activation checkpointing in SimpleFSDP. So what is the reason for selective activation checkpointing? So typically, when you have a neural network, you'll have like a lot of things going on, but for the most part, I think 60% of operations are oftentimes just matrix multiplications, right? And if we just zoom into a particular matrix multiplication, like what actually happens? You have some input A, you have some input B, you do a mapmul, and then you get out a tensor, which represents your activation. And this activation will then feed into the rest of your network. Now, sometime in the future, the operation that you fed your activation into we're going to have to calculate the derivative of it. And so there's going to be some incoming gradient that came from the rest of the network. And to calculate the more gradients, we're going to need this activation. So traditionally, we just save this activation, this tensor, in the forwards. And so in the backwards, we can just read from it. Now, it turns out that modern GPUs are really fast. And sometimes it's actually fine to just completely redo this computation. And so you don't have to save this activation at all. And so in practice, what it might look like is something like this, where when the gradient comes back, you don't actually have a tensor you read from. Instead, you just recalculate the activation and then use that in your derivative. And in theory, you can do this for every single activation. That's called full activation checkpointing. But it's pretty common nowadays to do what's called selective activation checkpointing, where you basically construct a policy to say which operations in your graph do you want to recompute and which ones do you actually want to save activations for. So let's take a look at the code. So again, we're in DeepSeek v3, and we see that if in the config we have activation checkpointing set, then we call it this apply AC function. And this apply AC function, there's two main paths, but let's just go for the common path. You see that for each transformer block, we do this wrapping thing again, where we call apply AC to transformer block. And then we'll wrap the transformer block in activation checkpointing. So if we go down here, we can see there's full AC. That's pretty simple. The one that we care about is the selective activation checkpointing. And the common route is to go to this. So this apply operation selective activation checkpointing. And if you look at this function, if we ignore this part, we can see that this is kind of where a lot of the magic happens. So at a high level, right, we specify this custom policy. And this is what I was talking about earlier, that it basically is a policy that tells us which of the operations we want to activation checkpoint. And then this is fed into the checkpoint wrapper. And if we look at the policy, it's kind of interesting. So here we see, if we have a 2 copy in the device on CPU, we must save it. Here we apply this heuristic, where we say, if the operation is a mapmul, then let's prefer recomputation. And then if the operation is in like a whitelist of operations that we want to save, then we call must save. And so this policy is used to figure out which of the nodes in our FX graph do we want to save versus recompute. Now, I'm not going to go into the details of this PTD checkpoint wrapper. I will point you to where it exists, though, which is it's just alias. So it's actually called checkpoint wrapper, and it's in PyTorch. So it's just here. So we can see here def checkpoint wrapper. And if you want, you can go into details on how this is implemented. But hopefully this was a good high-level overview of how SAC works conceptually, and gives you a few code pointers to read deeper if you're interested.